Okay. Yeah, I think it's recording. Okay, I think it's recording. All right, so today will be our last number theory lecture. So what I want to go over is how do you solve IMO problems? So the last few lectures were something about theory and so with number theory, once you know the theory and you know the techniques, how do you actually go about solving IMO problems? So the difficulty I'm thinking about is IMO problem 1-4 to easy 2-5, so that range. And that's the range that you guys should be try to solve problems at. Okay, so yeah. So let's start with so what are some common techniques? So hopefully you guys know these, but let's go over them. So okay, so one big technique is using modular arithmetic. If I have an equation or something, reducing it mod n. Okay, and so yeah, I listed some ideas for how do you choose the correct modulus, but let's do some problems where you can see. So yeah, so let's look at problem 1. The problem here is you have you want to find all prime numbers for which this expression, you want to find all prime numbers p for which there exists x, y, z, so that this expression is a product of exactly 3 distinct prime numbers. Okay.
We
So
can reduce the complexity of it since we know that there are certain primes that will always divide the expression.
okay, that's right. So the idea is you want to show that there are some primes that will always divide. So which primes will always divide? Let's
Well,
start with that.
for starters, P will always divide it by Fermat's little theorem.
Exactly, yeah. So the first thing is so if you consider it mod p, you'll get that p always divides by Fermat's last little theorem, right? And the
Also,
idea is
since we have, oh,
yeah, go ahead.
I was gonna say since we have six terms and each two share parity, then it's always even. So we know that it's divisible by two as well.
Okay, excellent. So the point is if I look now at mod 2 parity, I can also find, okay, so what do I find? So x to the p and x have the same parity, y to the p and y have the same parity, z to the p and z have the same parity, so it's always divisible by 2. Okay.
And since we test by two by hand, which is easy to show, then for any odd prime bigger than two, since the modulars of, for example, if x is congruent to one, mod any odd mod three, since p
Mm-hmm.
is an odd number, then x to the p will also be congruent to one, and if x is congruent to two, then x to the power of p will also be congruent to two. So we know that x to the power of p and x are congruent to the same number modular 3, so the entire thing is mod 0, is congruent to 0 mod 3. So it's also divisible by 3.
Okay, great. So now we consider mod 3, and what you're saying is you're claiming that x to the p is congruent to x mod 3.
Yeah.
And is it true? So, okay, if x equals 0, if x is 0, it's true. And now, okay, if x is 1, it's true. Okay. And if x is 2, okay, there's a slight problem. So it's not always true. It's if p is
Yeah, I
if
assume
p is
that p
odd,
is
right?
odd.
Yeah, well,
And
so okay,
2,
almost always.
fuck.
We have to worry about the prime p equals 2. Yeah, so as long as p is odd, then yeah. So if p odd, then it's true, right?
For 2, we can just demonstrate a case. That's why I excluded.
Okay, yeah, so that's a good point. So the point is, okay, so p equals 2, we can so for p equals 2, we can find such okay, we basically we have to find x, y, z explicitly, right? Okay, so we okay, but the point is for p equals 2, you have to find explicitly a solution. So okay, so we can maybe ignore that case for now, but yeah, it says you're saying for any other prime, what do we do? So by looking at it mod 2, 3, and p, we find that these are always prime factors. Okay, great.
So now
So
we
what does
put
it
that the
tell?
equation is equal to 6p, and we want to find if there's a p that satisfies that.
Yeah, great. So okay, but one more point is okay, maybe we should, there's another case you have to exclude, right? There's like p equals 3 as well, right? Because otherwise these are the same. Like p equals mod p and mod 3 are the same. So maybe also p equals 3 we exclude. Okay, fine.
Yeah, we
But
can
yes,
do that.
yeah, so that case, okay, if that's not true, then what do we need? We need this expression. So maybe I'll start a new page. If that's not the case, then we need, okay, so p doesn't equal 2 or 3, then we need 6p equals x to the p minus, sorry. Yeah. Great. And, okay. So now what?
So we know that at least one of the three numbers must be equal or bigger to 2, since having x is equal to y equal to z equal 1 doesn't work. So we assume without loss of generosity that x is bigger or equal to 2.
Okay, great.
So we group the x to the power of p and the minus x, and we know that 6 times p is larger or equal to xp minus x, which is 2 multiplied by 2p minus 1 minus 1.
But 2 times 2p
We
minus
just
1, what,
factor
like
it.
this?
No, p as a power.
I see. Okay, yes, yes, yes. Like this?
Yeah, but you put x to the p minus p, it should be x to the p minus x. Also
Yes,
2 to the
sorry.
p minus 2.
Yes, yes, that's right. X to the p minus x to the p minus 2, and then, so maybe you want to factor it or something?
Actually, we don't need the other part. I think we can just keep on the 2 to the p minus 2. We can just stay
Okay,
at
yeah.
2 to the p minus 2. And
Yeah,
we can show that 2 to the p minus 2 is larger than 6p for any number bigger than 6.
yeah, okay. So, yeah, so basically the point is should get a contradiction for large enough p, and in this case you said p greater than 6, right? Okay.
So the only case left here is to show that there exists or doesn't exist one for p is equal to 5.
Right, okay, so I guess, yeah, when we go back to the list of primes we excluded, we should now just check 2, 3, and 5, right?
Which
Okay.
we can show there,
So,
quite simple though.
yeah. Okay, yeah, so the point is, okay, you reduce it to just 2, 3, and 5, and in that case you can find, I think, explicitly some solution. Good. Okay, nice. Okay. Yeah. So yeah, so the point I guess was how do you know which prime to pick? Okay, so you should always try parity. You can always try 3. It works for some reason. And then since you see the exponent p, you try mod p. And you get whatever information you want. Okay, so let's look at the second one. Problem 2. Find all integer solutions to x to the 3 plus y to the 4 equals 7. So integer, not positive. If you said positive integer, then it's kind of not very interesting, but okay, integer, right? So x should be negative, I guess, right?
I'm pretty sure there doesn't exist any integers that satisfy this.
Why?
Uh, I'll, I wasn't really able to prove it directly, but
So
I
probably it.
guess mm,
Uh-huh. Right.
my way of thinking was I assumed that, for example, that x has to be congruent to either 0 or 1 or 2 up until 6. And I
Uh-huh.
showed that the only cases that work are x is congruent to 3 or 6, which
Uh-huh.
also implies that y has to be congruent to 1 or 6.
Uh-huh.
And after really long algebra, I don't know, it doesn't seem to work in the end. But I'm pretty sure
Well,
it could be solved in a simpler way.
okay, so you're considering mod 7, right? So let's think about that. So let's see what happens if you consider mod 7. So yeah, so let's consider mod 7. Okay, so we want x to the 3 plus y to the 4 equals 7, right? So, and you're saying if you considered mod 7, what do we get? So it's a good idea, right? Because, okay, then we get some nice equation like this. And now the question is, does this have solutions? Mod 7. Um,
I think it does. We have, no, it does, but it wouldn't be equal to 7. There, it wouldn't end up being 7, I think.
okay, well, you don't know because I mean, you just what am I? So there are solutions in mod 7. So it doesn't like you can't use that to deduce that there are no solutions. You see? Because you don't like, for example, what if y is some big number and x is some small, like very negative number? They could almost cancel, right? Like you can have y is something very big, x is something very small. Maybe you get exactly 7, right? So this doesn't. I mean, so there will be solutions, and I think you can do it by hand. I think one other way is to understand that. Okay, so what's happening with mod 7? Well, okay, first of all, there's solutions where x and y are both 0, mod 7. But actually, there are other solutions as well. Because one thing you can do is mod 7, um, there's a primitive root. So there's an a there like okay, there exists a such that the order of a mod 7 is exactly 6. Right? So okay, so we write x is equal to a to the k, and no, maybe that's not quite what I want. Maybe I don't. Yeah, okay, so what am I saying? So if this is true, okay, x cubed is a third power, right? So what it means is x cubed is congruent to plus or minus 1 mod 7 if x is not 0. Does it make sense why this is true?
Yeah.
Right? Because the sixth power will be 1, so x cubed is a square root of 1, so it's plus or minus 1. And then what? Then you're solving y to the fourth is congruent to plus or minus 1 mod 7. And there will be solutions, right? Because like okay, there will be many. You can sort of okay. Um, yeah, there will be solutions, I think. Maybe um okay, maybe let's not go down this road. Let's not really go down this road. So um okay. The the reason I included this example is to illustrate one point, which is, okay, this problem is a little bit, you have to pick a modulus that maybe would not come to mind immediately. So, okay. If you want to show that this equation doesn't have a solution mod p, right, for some prime p, so we'd consider x cubed plus y to the fourth is congruent to 7 mod p. You would need to pick a prime p where there's not very many third powers or fourth powers. Like with 7, okay, there's not very many third powers, but there's a lot of fourth powers, right? Because maybe let me ask a side question. This is kind of important. So, how many fourth powers? Like, okay, so basically, how many values can y to the fourth take mod 7? So maybe if we understand this question, maybe this will make sense. So, how many values can y to the fourth take mod 7? Does it make sense what the question is?
We have 1. We also have 2.
Well, okay, you can list them, but there's a way to do it without listing them out. Like the key
Actually,
point is we like for every prime there's a primitive root, so there's a number whose order is exactly p minus 1.
We can raise y to the fourth to the 3,
Huh?
maybe. And we have it's divisible by 6. And so
Okay.
if we assume that 7 does not divide y, so we have y to the 12 is congruent to 1 with 7. And that implies that y to the 4 cube minus 1 is congruent to 0 with 7. And then we can vector this. And we have y to the 4 minus 1 times y to the 8 plus y to the 4 plus 1 is congruent to 0 mod 7. One of these must be 0 mod 7. The first one gives us that y to the 4 is congruent to 1 mod 7. And the second maybe we can let y to the 4 equal x. We have x squared plus x plus 1 is congruent
So
to 0 mod 7.
I called it the so that doesn't conflict with the other notation. But
Okay.
yeah.
Then,
So you're actually yeah.
And then maybe we can vector this. It's like it's a polynomial, and maybe we can vector it mod 7.
Yeah, so you can actually factor in mod 7, and actually it's true that if I have a degree n polynomial in mod p, there's at most n solutions. This is true. So yeah, you can factor it if you just found one solution. But actually, I don't want to go that route. There's actually an easier way to understand how many values y to the fourth can take. There's
So we can now deduce that there are at most 4 values.
Oh, sorry, yeah. So there should be at most 4 values. Yeah, go ahead.
Because we have 1 and we have 0, and from this polynomial we get at most two solutions. So at most we will have 4 solutions.
Yeah, exactly. So at most 4. And it actually turns out to be exactly 4. But maybe let me give an argument that actually just gives you exactly the number of solutions. So the key thing is you have to use this fact that there is a number with order exactly 6. I didn't prove it before because the proof is hard, but you can use this fact. So for any prime, we know the order always of any number always divides p minus 1, but there's a theorem that says there's always a residue that has order exactly p minus 1. Okay, so what is the consequence of this? So yeah, so let me explain the point. So yeah, so I'm saying there exists a basically not equal to 0 mod 7 such that the order of a mod 7 is exactly 6. So it means that if I take the powers of a, so there's going to be a to the 0, which is 1, and then there's a squared, all the way to maybe we don't start, maybe we start with a squared, and the last one will be a to the p minus 1, which is in this case a to the 6th. Okay, well, maybe that's a to the p minus 1. Okay, so these are all distinct, right? Because if any two are the same, the order would be less than p minus 1. So the point is, since they're all distinct, this should be as a set equivalent to 1, 2, all the way to p minus 1. Does it make sense? What I'm saying?
Yes.
So now actually it's not so hard to understand what the fourth powers are, because what does it mean if something is fourth power? So y to the fourth, right? So let's write y is congruent to a to the power of k. So okay. So either y equals 0, one thing, or y is some power of k, some power of a. And then y to the fourth is going to be a multiple of 4 power of k. Okay, so what are the values it can take? Well, the point is okay, we can take a to the fourth, a to the 8th, a to the 12th. But then that's it, right? Because the exponent is mod 6. Does it make sense what I'm saying? This is the same as a to the 0. Does it make sense what I'm saying?
Yes.
Yeah, okay. So like what I'm saying is if you want to understand like what are the say like powers of what are the elf powers modulo p. Okay, the point is it's the number. So okay, there's always going to be like, or maybe I pass how many elf powers. Okay, the point is that there will always be, there will be 1 from 0, and then the rest is going to be what? It's going to be p minus 1 divided by GCD of p minus 1 and L is the number of elf powers. Does it make sense? Should I explain more, or it makes sense?
But why?
Because so what are the so the one, okay, this one you understand, this one is just 0, but the rest of them I'm asking, okay, like what are the elf powers modulo p? They're going to be a to the L, oh sorry, no, not a, there's no a, it's a to the L, a to the 2L, and so on, right? So what am I asking? I'm asking how many multiples of L mod p minus 1, right? Because the x1 is taken mod p minus 1. And the answer to that question is p minus 1 over GCD p minus 1 comma L. Does it make sense? Maybe like
Yeah,
okay,
yeah,
like the point is like what's the first multiple of L that will actually be divisible by p minus 1? It's going to be exactly this number. Like the last one here will be a to the power of L times p minus 1 over the GCD. Does it make sense?
Yes, but are we assuming that the order is b minus 1?
So we're assuming that we've picked a number a whose order is p minus 1. So that's basically, there's a theorem that says there will always be, for any prime, there's a number with order p minus 1. It's called, so this is what we call a primitive root. And so so you're right, I'm using this theorem. I'm using this, and you can use this theorem, on IMO. But okay, so I didn't cover the proof of this theorem, but I'm saying if you know this theorem, then it's very easy to understand how many Lth powers there are mod p. Like, does it make sense?
Yes, so I see, because these two sets are congruent mod b.
You suppose what?
Yes, that's because these two sets are congruent mod b.
Yes. So that's equivalent to being a primitive root. Yes. That's the idea. But you see, from the primitive root, this follows, right?
Yes.
Yeah. So okay. So why did I so what was the point of this? The point of this was just I wanted to what I want to do? I wanted to explain something which is like sometimes when you think about picking a modulus, you should think so okay, like let's go to the problem we had before. It was here, right? If I want to pick a modulus P where this does not have, where I want to show this doesn't have a solution, you want to pick a modulus where x cubed and y to the fourth. I mean, okay, if you can get, like if you can get these to be p minus 1, that's great, but that's kind of hard. So what we want to pick a modulus where these are both divisors of p minus 1, because then there will be a big restriction on the number of powers.
So 13.
Yeah, so exactly. So the trick is to pick p equals
Mod 13. So,
Yeah,
and
mod
we
13.
show that there doesn't exist x cubed and y to the 4 such that their addition is equal to congruent 7 with 13.
Yeah, exactly.
Right.
And yeah, exactly. And so what actually happens? So yeah, there will be what? There will be 4 values for x cubed, and there will be, okay, I should write it in a different way. So there will be there will be 0, but excluding 0, there will be 4 values and 0, and then here there will be 3 values and 0. And okay, the point is when you calculate it, when you list them out, you can actually see that there will be no solution mod 7 or mod 13. Okay. It's yeah, okay. You can do the exercise. I don't know. I'm not sure it's very useful for us to do it. Yeah, but okay, you will find that there's no solution mod 13. Okay. No, that's not what I want to do. Sorry. Okay. Now, okay, so let's look at this next idea here. So now I want to say something about factorization. So do you guys know all of these so I'm sure you know these 3, but do you guys know what I mean by Simon's favorite factoring trick? Have you heard of this before?
I tried searching it up, and the only thing I found is completing the rectangle, and I didn't get what that was.
Yeah, that's what it is. So yeah, it's kind of okay. It's something I think it's you have to know just because it shows up sometimes. So let me just show the standard example. So yeah, so what's the standard? So the standard example is something like find all. Yeah, so the standard example is like this. Okay, so find all integers. This is the example of Simon's favorite factoring trick. It's called SFFT. Okay, so find all integers x and y such that 1 over x plus 1 over y is equal to, let's say, 5 over 6. Okay. Okay. This is a very classic problem. So how do you solve it?
Do we multiply by x, y, and
So
just
the first
put
step is not doing anything very clever. You just multiply it all out because it's kind of okay. We multiply everything together. So what do we get? 6x plus 6y equals 5xy, right? Okay. So now, okay, this is what, if I didn't know this trick, I would have no idea how to do this problem, but okay, there's a thing where anytime you have some kind of quadratic term in linear terms, you can do this. So let's see, what's the point? The point is I want to make this expression into something that's factored. So what do I do? Let's do it like this. So it's xy minus 6 over 5x minus 6 over 5y equals 0. And so I write it like this. X minus 6 over 5 times y minus 6 over 5 equals 36 over 25, like this. Okay. It's what you call completing the rectangle. It makes sense, yeah, what I've done here. It makes sense, yeah.
yeah. It's just quite interesting.
Yeah. So okay, the point is now okay. I can I get rid of the denominators because they're not numbers. Okay, so now what? This is what I have, and now this problem is much easier to solve because okay, but now do you see how to solve it? It's you can just search over the factors of 36 and kind of. Does it make sense?
Yeah, it does.
Okay, so this is called completing the rectangle or Simon's favorite factoring trick. So this is something that okay shows up a lot in Olympiad. So okay, there's a homework problem on this. I don't know if I want to spoil which one it is, but one of the homework problems is about this. So it kind of sneaks up somehow. Okay, and okay. And do you guys know about this Sophie Germain's identity? I wrote it wrong. It should be 4y to the fourth. But do you guys know this identity?
No, this I haven't encountered before.
Yeah, so it's kind of okay. It's also something let's see. Okay, it's just something that shows up. I'm trying to think where. It's in one of the homework problems, I think. Yeah, you will see. It's maybe one of. You will see. It shows up as one of the homework problems. Okay, but. So let me just explain what the identity is, and then, okay. So the point is, okay, like we know how to factor things like x to the n minus 1. So for example, if I get like x to the 8 minus 1, okay, how does it factor? I get x to the 4th minus 1 times x to the 4th plus 1. And okay, then I also have, okay, I can further factor this one, but the point is this term here, like this is the cyclotomic term, if you know what I mean, but if you don't, it's okay. This term it doesn't factor in general. But sometimes you can make it factor. So if I have like x to the 4th plus 4a to the 4th, so I'm thinking of a as some kind of constant, this does factor. So the point is, okay, x to the 4th plus a, for general a won't factor, but for some types of a, for some forms of the number, it will factor. And the way you sort of realize that is you say, okay, this one is equal to x squared plus 2a squared squared. Right? That's just that'll give me these terms. And what's the left over? So what's left over is 4 times x squared a squared. Yeah. And the point is, this is a difference of squares. So it's factors. Right, so this is equal to x squared plus 2a squared squared minus 2ax squared. Okay, so this is equal to x squared plus 2ax plus 2a squared times x squared minus 2ax plus a squared, 2a squared.
That's very neat, actually.
Very nice. It's a very nice thing, right? Because usually you see something like x to the 4th plus, like if you see x to the 4th minus something, okay, if I see x to the 4th minus something, okay, maybe there's something, if I can show a is a square number or a 4th power, I can factor it. But when I see x to the 4th plus something, it's not, usually you can't factor it, but you can get lucky. You know, there's this sort of very, you know, looks like it came out of the blue factorization, but it's nice. Okay, so this is called Sophie Germain's identity. It's also something that appears a lot in Olympiad problems. Okay, so, all right. So, yeah, so probably these are the new things that you didn't know about, but okay, you know them now. But I want to do one problem where that illustrates how to you know some sort of unexpected uses of factorization. So yeah. If you see something that you can factor, great, but sometimes you don't. So okay, if I look at this equation, 3 to the x minus 2 to the y equals 5. I don't immediately see anything that can be factored here. Right? So what are some ideas?
We
how you
do
can
know
solve
that
this?
x has to be smaller than y, though. So we can write
Yeah,
y as ax plus b.
yeah, so okay, y can be, you can shit y is okay, so you want to do something like this. So you want to say
And for x
y
bigger than
is
2, if there exists a solution, y must be bigger than x.
yeah, right, that's true. So you can get y bigger than x.
I
But
then,
okay,
I think, showed that the first term in the product, when you factor them, is bigger than 5, so the entire term is bigger
but
than
how
5.
do you factor this is my question.
First, assume that b would be 0, then you
Okay,
can
then it
just
factors, yeah.
take then it factors, and it's easily shown that the term would be bigger than 5.
Okay.
For
What
B
if
not equals 0, I haven't done that yet.
okay, so yeah, so the okay, but okay, good. So yeah, so B equals 0, you can factor this because they're both x powers. But what if they're not? But yeah, but you know, so in general, this B it can be anything between 0 and a minus 1. So there's a lot of other cases to consider. But you bring up a good point, which is sometimes if you have control over the exponent, then you can show that it factors. You see, so in this case, what did you do? So okay, like you have x and ax, the point is the exponents have a common factor. So if the exponents have a common factor, like they're both whatever, divisible by 5 or whatever, they're both divisible by something, then you can factor this expression. So sometimes when you see an expression like this, which is a difference of powers, you can get some hope where if I can show x and y are both multiples of something, then you can factor it. So what can you do here? Okay, let's take a yeah, so you have a break at 5:40, so let's take maybe a 10-minute break or something, and then I'll explain how to finish this problem. So maybe we'll resume in what? Let's say at
I think
sorry?
I think I have an idea. Maybe we can
Okay.
consider like we have order of 3 mod 5 equal order of 2 mod 5, which is equal to 4. Maybe that would help us.
Okay,
We
so
have
you're saying
we have
you're
4
considering mod
values
5.
x.
Okay, so your idea is to consider mod 5, right? So let's do that. Let's see what we can get from mod 5.
Yeah, they both cycle every fourth power.
So I think they're both maybe primitive roots, maybe, I'm not sure. So let's see, okay. So 3 to the x minus 2 to the y equals 5. And your idea is, okay, let's consider mod 5. So, okay.
We would now we just consider all the values of 3 to the x and 2 to the y, and we will get that 2 divides both x and y.
Okay, so let's see. Why do we know this? So let's see. So the powers of 3, they go 1, 3. Okay, so 1, 3, and then 9, which is 4, and then 12, which is 2. Okay. And y 2 goes 1, 2, 4, 3. And so
No,
why do we get that they're both even?
here we should have that 3 to the x must be 4 and 2 to the y must be 4, and that implies that x and y are both must be congruent to 2 mod 4.
But why can't we have this? Why can't we have like right? Why can't we have like x is 1 mod 4 and y is 3 mod
Let's
4?
see.
I think it works, right? If they're both, if one is 1 and 3, for example. So it almost works. It almost gives that they have the same parity, but maybe they're both odd, right? Does it make sense? Oh.
Yes.
Yeah, okay. But it's a good start. So okay. But you bring up a good point. Like if they're both even, we actually win because if they're both even, we can factor this expression and it actually becomes very easy. So, okay, so if you can show they're both even, that's a very good thing. So we know they have the same parity. So if we can show one is even, it's enough. Yeah, so is there some way to show that one of them is even? So let's look at our list of how to pick a modulus. You should always try 2. I'm not sure if 2 helps us that much here because I'm not sure parity will help us very much. Maybe it will. I don't know. If you try parity, we get odd minus even is odd, yet not very helpful. But the second hint here, to always try mod 3, right? I don't know. So if you try mod 3, does it help? So mod 3, we get 2 to the y is congruent to 1, right?
To 1. And so
Is this right?
y is even.
Yeah, y is even. Okay.
And so
Then
it's
we also
even.
x is even. Great. So now it's great. Now we have they're both even, and we can do something great. We can say, okay, we say 3 to the power of 2a minus 2 to the power of 2b equals 5, and we can actually factor it now. 3 to the a minus 2 to the b times 3 to the a plus 2 to the b is 5. Okay, and look, now it's clear. One of them is 5, one of them is 1, and you can figure it out from here, I think. Okay, great. So any questions about these first few techniques? Okay, so then let's take a 10-minute break, yeah? So it's what, 53, so at 03 we'll resume. Okay. Resume recording. Okay, I think it's recording. Great, so yeah, so now let's talk about the third very common technique, which is counting the exponent of a prime, okay? So if a prime divides something, how many times does it divide? Okay, so there are some formulas that maybe you know already, but I just want to state them. So, okay, if I have n factorial, how do I count the number of the power of p? How do I count the valuation? It's this expression. Do you guys know this formula and how to prove it?
No,
Yes.
but I've never seen it before.
Okay, so let's then I should explain it. So let's say I wanted to know like v3 of like 100 factorial. Okay, so how many powers of 3 will I see in 100 factorial? Well, I multiply it out. For every power of 3, I see one power. Like for every multiple of 3 between 0 and 100, I see a power of 3, right? So first I'll look at 100 over 3, 4. This is the multiples of 3. So this is counting 3, 6, all the way to 99. Each of these contributes 1 power of 3. Okay. But this is not enough because there will be some multiples of 9. Those will contribute an additional multiple of 3, right? So I have to do 100 over 9. This will count 9, 18, 27. All the multiples of 9.
Oh, yeah, I see it now.
Right? And then I keep going, right? Because now, okay, but still it's not enough because now multiples of 27 will contribute even one more power of 3, right? So, and I do this. And it's not really an infinite sum because, you know, eventually it's 0, right? Like
What's
I don't
zero?
have to, okay. Yeah, like 1 over 81, and then after that I just stop, right? There's no fifth part of the three. But okay. So that's this formula. Okay. Great. So one way to, well, okay, first of all, let's sort of, what does this mean basically? Yeah, so what's happening? So what exactly is happening here? Okay. When I look at this expression, okay, one thing is I want to have a little bit more space. So let's start a new page. So right, so we're talking about VP of n factorial, and we know it's equal to n over p floored plus n over p squared floored, and so on. So there are some bounds that we get. Okay, so one of them, for example, is we get VP of n factorial is at least n minus p minus 1 over p. That's just if you just consider this term. But there's an upper bound, which is n over p plus n over p squared plus all the way, right? Where I just ignore the floors. And what is this? Well, this is equal to n times a geometric series. Okay. And what does this geometric series sum to? Well, we should calculate it. It's going to end up being 1 over p minus 1. So it's n over p minus 1, right? How does it work? You take 1 over p factors out, and it's 1 minus 1 over p, and this is equal to 1 over p minus 1. Right, so that's what this is. So it means, yeah, so it means the number of parts of p is approximately n over p minus 1, but you have to subtract some stuff because we took floors. Okay, and then what's maybe it's called a lemma. What's the lemma say? The amount you subtract is exactly given by this thing called SP of n, where SP of n is the sum of the digits of n in base p. Okay. Okay. And maybe I can leave it as homework or something to prove this. I don't know. It's not so hard because you just, okay, I take n, I write it in base p. It looks like a d minus 1 all the way to a0 in base p. And how do I take floor? It's okay, okay. What is n over p floored? It's going to be exactly the number where I delete the last digit, right? And then like n over p squared floors means I delete the last 2 digits. Does it make sense what I'm saying?
Yes.
Okay. And so if you just play around with this, you'll understand how to prove this formula. It's not hard. So any questions about that? Okay, so that's the explanation of these two formulas. And now, okay. Great. So, and of course, there's lifting the exponent. Yeah, okay, which we talked about before. But yeah, so these are the main tools for counting exponents. Let's look at some problems. So, yeah. So actually, maybe let me ask. So, Karam, have you seen this problem before? Problem 4?
I think yes. I saw
Okay,
it before.
okay. So because I already I was discussing with Adam before. So if you want, maybe should we skip it?
Yes, I understand the solution of it.
Okay, yeah. So let's skip problem 4 because we discussed it. So now let's look at problem 5. Yeah, so this is a nice problem. So we want to solve this equation, Diophantine equation, where a, b, c, n are all positive integers, right? So 2a to the n plus 3b to the n equals 4c to the n. Okay. Two a to the n plus 3b to the n equals 4c to the n. All positive integers. So any ideas, where can we start? Maybe does it remind you of any other problem?
Similar to the ones we did above.
Because of the
Please
powers, right? Yeah, so there's this thing with powers, right? Now, the thing about powers is, okay, let's think, how can we factor things like this? So for example, if we could get n to be even, this will be a square. But I don't know how to make these guys squares, right? So I don't know if there's an easy way to make these things be factorable, right? Like usually things will factor if there's a pure power. Like if I have something like just a to the n plus b to the n, maybe there's some chance it factors, right? But or maybe, you know, with Sophie Germain, there's okay, it's not a pure power, but whatever, like one of them is a power, right? So it's kind of, it's not immediately clear to me that can get things to factor. But okay, there's something you should try before factoring, right? There's like, there's some information I think you can get from parity.
B has to be even.
Okay, so from parity, we just get b is even, right? Okay.
So we can
Always
rewrite 3b to the n as
that's maybe what letter we use. D, maybe, I don't know. 2d to the n. Okay, now what happens?
now they're
So the point is, I think we can use parity again, right? Because let's yeah, so n is at most, let's assume n is at least 2. Okay. Well, okay, let's maybe we don't even do that. Let's just start with this. So I can take out factors of 2. I get a to the n plus 3 times 2 to the n minus 1 times d to the n equals 2c to the n. Right? So now as long as n is at least 2, I can use parity again, right?
A also has to be even.
Right, so then a is even. And now if a is even, what happens? I can write 2e to the n plus 3 times 2 to the n minus 1 d equals 2c to the n. And now what? So now you can take out more factors of 2. We get 2 to the n minus 1 e to the n plus 3 times 2 to the n minus 2d.
To the n, we should put d to the n.
D to the n, yes, I forgot about this.
It's equal to c to the n.
C to the n.
So c has to be even too.
Okay, and c is even. Great. So if a, b, c are all even, what does it mean? So it means if we have a solution A, comma B, comma C, they're all even. So okay, what's the point? Okay. Look, let's think of it a little bit. So if we've shown that if we have a solution A, B, C, then A, B, and C are all even. I think that actually tells you a lot. Maybe I assumed n is at least 2, right? So okay, we're assuming n is at least 2. That's important. Assuming n is at least 2, we know that if there's a solution A, B, C, then it implies that A, B, C all even. What does that tell us about? So have you guys seen this proof that the square root of 2 is not rational?
Yeah.
So how does that proof go? It's similar to this problem.
Really?
So how do we prove square root of 2 is not rational? Okay, so
There are
suppose
multiple
square
ways
root
to
of
do
2.
that.
Okay, so but one way is like this. So suppose it's true, then we have x squared equals 2y squared. And what's the point? So now it means x is even. But if x is even, then y is also even. So usually, right? So okay, so this means x even. But then what? Then if x is even, then you write it as like 2a squared equals 2y squared, and so y squared, a squared equals, sorry, 2a squared equals y squared, and so y is even. And then use infinite descent, right?
Yeah, we can also do it by the rational root theorem.
Oh yeah, there's no even, but I'm saying, but yeah, it's true. You can use rational root theorem, but yeah, my point is, I'm illustrating. This is the technique you usually use here is infinite descent, right? Like if I have a solution, then they're both even, and then, but that works here as well, right? Like what we're saying is if we have like if you have a solution A, B, C, they're all even. You can divide by 2 all of them, and you'll still have a solution because this equation is homogeneous, degree n, in A, B, and C. Like if A, B, and C give you a solution, then dividing by 2 also
Yeah,
gives you a
because we
solution.
took 2 to the n. Yeah, yeah.
Do you see?
Yeah.
So it means if I have this, but then there cannot be, because then you run into the infinite descent problem, because if you have A, B, C are all even, I divide by 2, I get another solution. Those are all even, and then so on and so forth.
So it's 0.
Yeah, it means A, B, and C would have to be 0, right? Does it make sense what I'm saying?
Yeah, yeah.
Karam, does it make sense? How this is infinite descent?
Yes.
But yeah, okay, so it shows that if n is at least 2, then there's no solutions. Okay. But okay, but I didn't really use, I said this problem is about counting exponents. I didn't really use counting exponents. So let's say I change the problem slightly. So instead, I said this. I say, find all solutions to actually maybe it's still okay. No, that will still actually be the same. let me just maybe say what I was trying to say. So I don't think changing the problem will. Okay, what I'll explain is this. There's another way to solve this where you just count exponents. So the solution before was by infinite descent, but there's another way where what I can do is I can say let's count the number of powers of 2 on both sides. So let's compare v2 of 4c to the n. Let's compare it with v2 of 2a to the n plus 3b to the n. Okay. So what will this be? This one will be what? It'll be however many, whatever the valuation of c is, times n plus 2, right? That's the left-hand side.
Mhm.
But what will be the right-hand side? So, okay, we can look at the two terms individually, right? So this like 2a to the n, its valuation will be n times the valuation of 2 of a plus 1, and the valuation of this one will be n times the valuation of b plus 1 plus 2 plus 0 plus 0, right?
3.
Yeah, plus 0, right? Now, using this information, can you determine the valuation of this?
Oh, we couldn't add stuff with them.
Sorry? So
we can tell that isn't there an equation that says that VP for x plus y is equal if VPX isn't equal to VPY?
yeah, exactly, right? So so this is a general. If I had an odd number and an even number, the sum is odd, right? The generalization is if I have two numbers x and y, where v2 of x and v2 of y, it can be p actually, where let's say VP of x is less than VP of y, so y has more powers of p, then it tells you that the sum has valuation
VP
equal to v of x, right? The smaller one. Does it make sense? Right? It's just so if I apply that
But we
here,
can't assume that one's bigger than the other.
well, okay, we don't know which one is bigger, but can they be equal is the question.
No, they
Can these
cannot
two
be
valuations
equal.
be? Why not?
Because we have n on both sides, and you can't have x plus 1 is equal. Oh no, I can't really express it properly, but they cannot be equal.
So these cannot be equal. I mean, the reason is
no, there's no unless they cannot be equal.
so okay. So can these be equal? There's a very simple reason these cannot be equal. Well, okay,
Only when
assuming
n is 1.
Yeah, when n is 1, they can be equal. So the point is this is 0 mod n, and this is 1 mod n. So as long as n is greater than or equal to 2, these two numbers are just different numbers, mod n. So they cannot be equal. Does it make sense?
So we assume that's either this or that.
Exactly.
We
So the
look at
valuation
both
here is
cases
one of
separately.
these two. Yeah, yeah, you can consider them separately. So it's either this is equal to either this or this. But what does it mean? It means either this equals this
Or this
or
equals
this equals this. But those cannot be true for the same reason, right? They're all different in mod n, as long as n is more than 3. As long as you also assume n is more than 3, these numbers are all different mod n. So no two can be equal. Does it make sense? What I'm saying? So if n is at least 2, then v2 of 2a to the n plus 3b to the n is equal to n v2 of A plus 1 or n v2 of B. And then if n is at least 3, then both these numbers are different from n v2 of C plus 2, just because they're all different.
Yes, so we look at n's 1, and I think we wouldn't find a solution there, so it implies that do you have to
for
be
n equals
0?
1, I think there is a solution, right? For n equals 1.
2, 0.
For n equals 1, I just have 2a plus 3b equals 4c, right? So
Oh, yeah, we can have that. It's easy.
yeah, what can we have? We can have, there's some solution. I don't know. I have to think. But, there will be a solution.
There are infinite
And then
solutions because it's homogeneous.
yeah, there will
And a
be
triplet
infinitely many.
ABC is the same as AB. I mean, DA, DB, DC.
Yeah. So there will be multiple. Okay, so how did I phrase the question? Maybe I should have phrased it as find all n for which there exists a solution.
Yeah, but
Yeah,
so we have
determine all
n
n.
is equal to 1 and n is equal to, that's it.
Yeah, so n equals 1, n equals 2. And I think you have to find something for n equals 2. I don't know. There's some you can do it. Okay, yeah, n equals 1, n equals 2. Yeah. Okay, so any questions about that? Let's see. Okay, so let's now look at. Great. So let's look at. Okay, so I wanted to explain one other thing, which is about bounding. So what is the idea behind this bounding and inequalities? It's just sometimes you can argue that two things cannot be equal because they're not of the same size. They cannot be of the same size. And so one very common way is will be illustrated with this problem 6. Okay, but maybe before we do problem 6, let me give an even simpler example. This is the most okay. This is a very classic thing. So let's consider the problem. Find all positive integers n for which n squared plus n is a square number. Okay, so you want n squared plus n equals m squared, where n and m are positive integers. Okay, so how would you solve this?
I think that there are no such n
Why?
because we can like we have n squared plus n is less than n squared plus 2n plus 1, and n squared plus n is bigger than n squared.
Great.
And so we have it's between two consecutive squares.
Great. So so since this number is between two consecutive squares, it cannot be a square. And so this is some kind of very common technique. Sometimes you can just use inequalities to show that something is impossible. So so there's a slight variation on this that I want to talk about. Yes, n squared minus 19n plus 89. So let's consider now the same thing. We want to now instead n squared minus 19n plus 89 is a square.
This is easy. We can just look at n minus 9 and n minus 10.
Right, so if you look at n minus 9 squared, it's equal to n squared minus 18n plus 81.
We know that, yeah.
But I don't know if this one is bigger or smaller, do I? Because wait,
We
do
don't
I
really
yes.
need to. We just look at n-9 and we observe that our term has to be between them. I mean n-10. We see that it's between them, so it's either n-9 or n-10.
So
And
your
you
claim is
just
that
show that
this,
it's 8 or 11.
but your claim is this, right? That it's less than -9 squared. Is that always true? Oh, okay, it's almost always true. Okay, it's true for which n? It's true if and only if what? N is more than 8, maybe. I think if n is more than 8, it's true. Okay, so it's almost always true. And the other side is
That's why I
that
put it between n-10 as well.
Yep. Okay, so what's the other? But we want to. But okay, so the claim is that it's between these two, right? So this one is like this, and for the other one, when is it true? So this one is n squared minus 20n plus 100, and what happens here? So this one is true if and only if n is at least 11. Okay, so this for n big enough, then it's between these two, and then it's impossible, right? And then you can check 1 through 11, I think, by hand. Okay.
We have that square for 8 and 11, though.
Ah, you're right. Yes, it is. Yeah, okay. So then, yeah, so okay. So basically, it's okay. There's n equals 8, n equals 11, and so we should check. Okay. So basically, we check n equals 1 through 11 by hand. Okay, great. Okay, so yeah, so you understand the idea. This is that's the idea. Now let's see let's do one more example of this idea. I think it's kind of a very common example. So, okay, let's look at find all into let's say positive integers a and b such that a squared plus 4b and b squared plus 4a are both squares. Okay. So both a squared plus 4b and b squared plus 4a should be squares. Any ideas?
I try to subtract them and see if I can factorize it into a difference between squares. But that didn't work.
Yeah, so I will say for this problem, there's a trick. There's a trick here. The solution is basically 1 line if you understand the trick. Nothing that clever has to be done. Or sorry. If you're something very clever, but you don't have to do that much work once you do it. It's not a very it's not a computation.
Do we write B in form of A or 1 in form of the other?
Yeah, so it's like this, right? Okay, here's the question. Let's say I pick numbers for A and B. I pick A equals 7 and B equals like 13 or something, right? Can you immediately exclude that one of these is not a square? So yeah, the point of this problem is just it becomes very easy if you just assume, without loss of generality, A is less than or equal to B. Because you can, because it's symmetric, right? If I want both of them to be squares, okay, I can assume A is less than or equal to B. Now what happens?
And we know that B squared plus 4A is always bigger than A squared plus 4B.
Yeah, so this one will be bigger, but I mean, this one you can basically trap almost between two squares, right? Because the point is this one is at least B squared. Well, it's strictly more than B squared. And it's less than or equal to B squared plus 4B, which is less than B plus 2 squared.
So it has
Does
to
it,
be
does it
B
make
plus
sense?
1 squared.
Yeah, exactly. But then, yeah, so B squared plus 4A equals B plus 1 squared. But that's not possible, right? Because one is even, like 4, you get this, right? So this is odd and this is even. So it's not possible.
Interesting.
Yeah, so it's kind of okay. It's the same idea as the other one, but it's kind of you need to do this. You need to assume A is less than B, right? So yeah. Okay. Let's see. So let's see how much time do we have. We don't have a lot of time, but let's start with this problem here. But okay, what I'll say about solving these IMO problems is that, at least at this difficulty, so the difficulty like from problems 1-4 to problems 2-5, usually each step is something you have seen before. It's one of these techniques, but what you need to do is you need to sort of chain a lot of these steps together. And so the problem is sort of about, you know, trying a lot of things, you know, in the right order. So let's look at an example. So I'm going to look at problem 9 first. Okay, so find all positive integers where this expression n times 2 to the n plus 1 is a square. Yeah, so let me find it here. So find all positive integers n so that this expression n times 2 to the n plus 1 is a square. So in other words, solve this in positive integers. So any idea where we can start? So remember, like,
Well, we know that the square of an odd number, so we can just substitute it and we end up with n to the 2n is 4a multiplied by a plus 1. So we can have 2 and minus. I don't know, I'm just trying stuff. I'm not sure.
yeah, so good. So let's try it. So let's say m equals 2k plus 1. And what did you get? You got, this is 4k squared plus, okay, let's say 4k, 4k squared plus 4k plus 1, right? And so now you got n times 2 to the n is equal to 4k times k plus 1. Is that right? Great. And this is very nice, right? Because actually we can remove well, okay,
now
maybe
we
not,
know
but
that no, we don't know.
I was gonna say we know n is at least 2, but not quite, but okay, let's not worry about it. So
You can
let's assume n is at
subtract. We
least
can
2.
divide by 4.
Yeah, so let's assume n is at least 2, and we get n times 2 to the n minus 2 is k times k plus 1. Okay. Great. What do we do with this?
So n multiplied by 2n minus 2 cannot be square itself.
But we don't have any
And
squares anymore, right? We have k times k plus 1. This doesn't have to be a...
yeah, which is why I'm saying it cannot be squared. So
Uh,
I think I have another idea. I think it might
okay.
work. It's
Okay, what's the other
related
idea?
to bounding.
Okay,
It's related to bounding.
okay.
We have is obviously is odd. We have n times 2 to the n equal to m squared minus 1, which equal to m minus 1 times m plus 1. And so we can conclude that the valuation of 2 to the n mod 2 is less than or equal to the valuation of m plus 1 plus the valuation of m minus 1 mod b. The valuation mod 2 I mean.
Yeah.
And one of these two valuations must be 1. We can take the two cases and maybe we could have a beautiful inequality.
Okay, so one of these must be 1, and your argument here is because they differ by 2, right? Is that the point?
Yes.
Okay, so great. So okay, so
And
one of
the
these,
left-hand side is n.
yeah. And the left-hand side is n. Right, that's right. So this is n. So what do we have? So it tells us that, okay, so you were telling us that
I think
okay, so
that we can conclude
and
that
like this, right?
yes.
Okay, great.
And then I think we can conclude that m is bigger than or equal to 2 to the n minus 2.
Right, so now we're saying m plus 1 is at least, so okay, we know m plus 1 is at least 2 to the n minus 1. Is that the first thing we're saying?
Yes, I think.
And then, right, because we know, okay, we know one of them is at least 2 to the n minus 1. So, yeah, so the worst case is if it's m plus 1. So that tells us m is at least 2 to the n minus 1 minus 1. Okay, and what's the other thing we have?
Which is bigger than 2 to the n minus 2. And then we substitute m with this. It's greater than. We don't.
So we put it here, you're saying, yes?
Yes.
Or maybe we can just put it even in the original equation. It's easy.
The original,
put it in
yes.
the original equation. Yeah, okay, so we put it here and this one together. We get what? 2 to the power of twice n minus 2 is bigger than or equal to. Is this what we have? Am I right?
Or bigger than. Bigger than.
Is it right what I have, or no? What am I saying? What I'm saying is wrong. So what? No. We are saying.
It's reversed.
I have it back. I wrote it backwards, right? What it is n times 2 to the n plus 1 equals m squared, which is bigger than or equal to 2 to the twice n minus 2. Like this?
We don't have the equality. We could say bigger than without the equality. Strictly bigger than.
Strictly bigger than, right? Because here it's actually right. So here it's strictly bigger. And well, is it so? Almost n could be 1, right? But okay, we assume n is at least 2. Okay, let's assume n is at least 2. Okay, then it's strict. And now what? So now it tells us that n times 2 to the n plus 1 is at least 2 to the twice n minus 2. And okay, so this
actually,
is okay. So
yes, we can consider
but
n is bigger than 3, bigger than or equal to 3.
Okay, so let's put n at least 3 then. Okay. Sorry. Let's put n is at least bigger than or equal to or bigger than?
Maybe bigger or equal than.
Okay, bigger or equal than 3. And now where do you want to put? Okay, so now here I want to put strictly bigger than, right? And I want to put strictly bigger than 2 to the, okay, yeah, so I want to do this. Strictly bigger than 2 to the twice n minus 2, like this. Okay.
I don't get why should n be odd? I think.
Where do we have n? M? Do you mean m or n or m?
N or maybe m. I feel.
Okay,
Did you
so
assume n
you're
was
saying,
odd?
yeah, so we are assuming m is odd, but that's okay, right? Because m has to be odd from here.
I think that yes, it has to be odd, but we don't assume that n is odd in the inequality.
No, you do assume m is odd here, because you are saying you need like one of them is right, like well, it's not, you're using the fact that
Yeah.
m is odd when you say that one of them is valuation 1, the other one
No.
is valuation n minus 1, right? I think so.
Yeah, I thought that you said n.
Okay, yeah. Yeah, so okay, maybe it's so m is odd. I don't know about n. N can be anything. I don't think we need n to be even or odd. Yeah, n can be anything. Okay. But yeah, okay, so I think we're here, right? This is where we are.
Now we have n times 2 to the n is bigger than or equal to 2 to the 2n minus 2.
2 to the 2n minus
minus
2
4, I
or
mean.
minus 4.
Mm.
Okay. Yeah. And then n is bigger than or equal to 2 to the n minus 4. And then what does it tell us? It tells us, okay, I guess we need to do some, okay, so
We
5
can
would
find
give
some
you,
bound.
yeah, I think maybe is it 5? No, 5 is already, no, 5 is, no, 5. Sorry, n is less than or equal to, it will tell us n is less than or equal to. And, okay, is 6 too big? Oh, 7. I think 7. 6 is too big. So
Maybe
if I do 7, I get, no, already 7 is too big, right? Because if I do 7, I get 7 is more than or equal to 8. So I think you get n at most 6. Is that right? I think so. Yeah, okay. So anyway, so n is almost 6. And then you can try all the small ones by hand. And maybe there's none, I think. Right, so 2 plus 1 is 3. No, okay, there's n equals 2, I guess, right? 2 times 4, yes. There's n equals 2, and I think maybe that's it. I don't know. Maybe it's n equals 2, I'm not sure, only. Yeah, I'm not sure. You check the first ones by hand, I'm not sure, but okay. Anyways, it's a very nice argument. The key thing is you know. So it's okay. Let's just go back a little. What are the steps? The first step was we have to factor, right? And so you see this expression, you see that how do I factor? You subtract the 1 over, right? Also, Adham, your method also works, right? Because when you get this factorization, you can do the same thing. You can say, look, you can say, okay, one of these is odd, the other one is even. So the one that's even is divisible by 2 to the n minus 2, and you can do some bounding. So yeah, did you guys see like the Adham solution can also be completed in the same way. Like once you have this expression, you can say that one of these is divisible by 2 to the n minus 2, and that gives you a very nice bound on everything.
Mhm.
Okay. All right, so any questions on this? Okay, so let's look at what did I want to do next? I wanted to look at this problem. Okay. Maybe this one. Let's look at this one. So this is from a previous IMO. Yeah, so here's the equation. You want to find integers so that okay, yeah, you can find all the integers so that k factorial is of this form, right? So it's 2 to the n minus 1 times 2 to the n minus 2 times, okay, like this. Any ideas where to start? There's some technique that this problem just screams that you should use.
We solved this problem the previous year.
Oh, we've done it. Okay, so you remember. Do you remember what the idea is? What the key idea is?
Yes, it's about the valuation.
Yeah, it's a problem about
The valuation
right?
of
So you look.
motto.
Yes, so it's the valuation of 2, right? So the 2. Yeah. Because why do we look at the valuation, the 2-adic valuation? Because okay, there's a lot of 2's here. Not only is there a lot of 2's, you can exactly count them. And here you can also count exactly the number of 2's. Okay, so since you've already seen this problem, maybe I should not do it. Okay. Okay, but okay, let me just give like the summary for Adam. So it's like this. So it's the point is you compare 2-adic valuations. Let's just write right-hand side. That's too much, right? So what is the valuation of the right-hand side? You know what it is exactly, right? Because you get 1 plus 2 all the way to n minus 1, right? That's the number of factors. And so this is exactly n times n minus 1 over 2. And for this one, it'll be some number, but okay, we can say basically, okay, what it's okay, the valuation here is less than n and more than n minus 1 over 2. That's what our inequalities say, right? It's pretty close to, it's somewhere around n, basically. And okay. So I meant K, like this. So the point is what? I don't know exactly what it is, but it means K is approximately n squared over 2. Or maybe even we can say K is approximately n squared even, like. So what is the point? I think the point is that we should expect the left-hand side to be bigger. So if this is true, it means the left-hand side should be bigger, right? So because why is this? If we take something like n squared factorial, what are we doing? We're multiplying n squared numbers that are all more than 2, whereas on the right-hand side, we're doing something like 2 to the n to the n, which is 2 to the n squared. So the left-hand side should be much bigger, right? Because here we're multiplying approximately 2 to the n, we're multiplying approximately like 2 approximately n squared times, whereas here we have something like n squared factorial. So the left-hand side should be bigger. Does it make sense, Adam, what I'm saying?
Yeah, I think so.
Okay. Okay, maybe okay. That's the idea. If you want some more, yeah, if you want some more details, please let me know. But I think yeah, Karam and everyone else has seen this problem from the training last year. I forgot about that.
Okay.
So let's look at
Actually,
yeah.
should not we here substitute with n squared over 2 factorial instead of n squared?
Yeah, you're right, because that's the lower bound, right? So you're right. So this argument is not, I left some details, but yeah, so what we should do, we should use what? We should use n times n minus 1 over, okay, yeah. So did use k is more than n times n minus 1 over 2. So we should say k factorial is more than n squared minus 1 over 2, or n times n minus 1 over 2 factorial. And then what we want to show is that this is true, right? We want to show this, right? Because then this is also bigger than 2 to the n minus 1 and all the way to 2 to the n minus 2 to the n minus 1. So the key inequality should be to show that this factorial here is more than 2 to the n squared. And you can show it. I think it's not incredibly hard. Okay. Okay. Maybe we have time for 1 or 2 more problems. So what do I want to go over? Let's look at, actually what I want to go over is this last one here. I think maybe problem 11 might be harder, but I want to do problem 12. Yeah, so it's this one here. Find all solutions to this. So it has a very nice idea. So let's look at, where did it go? This, yes. So find all integer solutions of this equation. X to the 7 minus 1 over x minus 1 is equal to y to the 5th minus 1. Any
This is
ideas
the
where
same
we
as
can?
saying x to the 6 plus x to the 5 up until 1 is equal to y to the 5 minus 1.
Great. So we can, it's the same as, yeah, we can write the left-hand side like this. And okay, there's a y-diff with minus 1. And okay, it's also, I don't know if it will be useful, but there's also the factorization of the right-hand side as well. Maybe it's useful, maybe it's not, I don't know. But yeah, any ideas?
I'm not sure, but I think maybe we considering the primes that divides the both of these maybe be helpful.
Yeah, that's a very good idea, right? So let's consider prime p, which divides both sides, right? Okay, great. So what does it mean? Well, on the left-hand side, it means, well, look, what does it mean? It means okay, it means x to the 7th is congruent to 1 mod p. Now, but is that enough? Like, is it enough that x to the 7th is congruent to 1 mod p? So, okay, so maybe let's think of it like this. Let's ask the question, what does it mean, or maybe, yeah, that p divides x to the 7th minus 1 over x minus 1? So certainly it can mean that, okay, so it means x to the 7th is congruent to 1 mod p. So one way of saying this is that the order mod p of x is, it divides 7, right? But it means it's
Not
either
the
equal to
order
7
is
or, well, okay, it's either 7 or 1. We don't know,
yeah.
right? We don't, it could be 1 as well. So here's my question, can the order be 1?
No, unless the number is 1.
So okay, so what we're asking is, can we have x congruent to 1 mod 7 or mod p?
No, since we have x minus 1 as the denominator and we cannot divide by 0.
Well, hold on. Let's be a little bit careful here, right?
I mean, unless x is less than p, that's the only case. But if x is bigger than p, then yeah, that's possible.
No, not necessarily, because you know, for example, I can write something like, I can say that let me think. I can let me just, okay. For example, 9 divided by 3 is congruent to 0 mod 3, right? So even if p divides the denominator, it can still divide the whole fraction. I don't know if, okay, but like my point is, you can't actually rule this out. Do you see what I'm saying?
Yeah.
Like it can be, like, p can divide x minus 1 and it can divide this both, right? But okay, is it possible?
If
Yeah.
if x is congruent to 1 would be, then we
Mm-hmm.
have x to 6 plus all these is congruent to 1 to 7 maybe would be.
That's right.
And we have B divides this, so B must be 7.
Yeah, exactly. So if this is true, then 7 is congruent to 0 mod P, and then P is 7. Okay, so it could be either P equals 7, then you can have if P equals 7, then you can have this case. But if P is not equal 7, then it must be like this. Okay?
Okay.
Does it make sense?
Yes.
So it's a very nice it's very nice. It's saying, okay, what are the divisors of this left-hand side? It's going to be primes. It can be either 7. We can worry about 7 later. Either it's 7 or it's primes where x has order exactly 7. Okay, so let's actually write this, right? So the answer, what does it mean that P divides this? So the answer is, it means that either P equals 7, and we'll worry about P equals 7 in a moment. Either P equals 7. Actually, what happens in the case P equals 7? P equals 7. Okay, we'll worry about it. Okay, either P equals 7 plus some other conditions, I don't know, or P does not equal 7, and the order of P of x is equal to 7, or is equal to, yeah, exactly, right? So, yeah. So there's two cases. So, okay. So but this tells you something. So what does it tell you? Like in this case, right? So if P is not 7, and then it means the orders of P of x is 7, it tells you something about those primes. What does it tell you?
That 7 divides P minus 1.
Yeah, it tells you 7 divides P minus 1. So those primes are all 1 mod 7. So in particular, P is congruent to 1 mod 7. So the divisors, the prime divisors of the left-hand side, there's some primes that are 1 mod 7, and there's maybe 7. That's what we get. Does it make sense?
Yeah.
Yeah. Okay, great. And now let's think. Yeah, maybe let's write that. I think it's important. So okay, so it's some kind of remark, I guess, right? Prime P dividing the left-hand side are P equals 7 or P is 1 mod 7. They all satisfy this, right? So right, so if P divides the left-hand side, then either P is 7 or P is 1 mod 7. Okay, so now let's look at the right-hand side, right? So yeah, so we got something from the left-hand side. Let's look now at the right-hand side. So so let's try this. From the left-hand side, we get P equals 7 or P is 1 mod 7. Okay, and now let's look at the right-hand side. So now what does it mean that P divides the right-hand side? Well, this is simpler. It just means y to the 5th is congruent to 1 mod P. So in particular, it just means, okay, it just means the order of is either 1 or 5, and we don't know anything else besides that. Okay. And if it's 1, it tells us y is congruent to 1 mod p. Okay. Any ideas what we can do from here?
Can't we use the fact that y minus 1 divides the left-hand side?
Okay, so what do we get from there? Y minus 1 divides...
The y is congruent to 1 or 2 mod 7.
Okay,
Since
let's
every
see.
divisor of the left-hand side has to be congruent to 1 mod 7 or congruent to 0 mod 7.
Okay, so I think the first thing you're saying is we should consider everything mod 7, right? So let's look.
Yeah.
So you're saying let's look a little closer at mod 7. Okay. And now you're saying, what do we know? Mod 7, we know that mod 7, we know...
We showed that if a prime divides the left-hand side, then it must be either 7 or congruent to 1 mod 7.
Yeah, exactly. Yeah, right. So it tells us that, right, great. So it tells us that y minus 1 is a product of primes that are either 7 or 1 mod 7. So, okay, so it tells us y minus 1 is either equal to 0 mod 7 or
Or
y minus 1 is congruent to 1 mod 7, right? This is right? Yeah, so great. So we get
yeah.
y is congruent to 1 or 2. Very good.
We also know that y to the 4 plus y to the 3 plus y, you get my point, is also congruent to either 0 or 1.
Very good.
And if we calculate it using either y is congruent to 1 or y congruent to 2, we get a contradiction. So y minus 1 cannot divide 7, so there doesn't exist any integers.
Okay, so very nice. So so we take great. So we take y equals 1. If we put it into here, what do we get? We get 5, which is not
Possible.
yeah, which is not possible, right? So
And we try 2,
yeah,
and it's also not possible.
okay, so we get here. Okay, so yeah, so there's 0, 1. So if we did this, we would get, for this side, we would get 5, and if we did 2, we would get, okay, we can do this 2 to the 5 minus 1 over 2
16,
minus
so
1.
2. Then we have 1 for 8, and we have 4 for plus 2 plus 1, and that's 3, 7, 8, 2, which is 10. We get congruent to 3, which cannot be possible, so there doesn't exist an integer.
Okay, excellent.
But
Okay,
how do we know that? How do we know that 7 divides y minus 1?
we don't.
Because
There are
y
two
minus
cases.
1 divides the left-hand side.
No, but we don't know 7 divides y minus 1. We just know that all the prime factors of y minus 1 are either 7 or 1 mod 7. But what's the result is that y minus 1 is either 0 mod 7 or 1 mod 7.
And then we substitute y with 1 or 2.
That with 1 or 2, and neither will
Okay.
give you either of them. So it's very clean. I think it's very nice. Yeah, so it's kind of, this problem is there's two steps. One is just think, okay, what primes can divide this? And you do that with some modular arithmetic. And then you look specifically at the prime 7 and you get something interesting. Okay, so it's a very it's very nice. So any questions about this? Okay, so which do I want to go over any of these? Here's what I'll do. I'll say, okay, this problem 11, it's a nice problem. But I think you know all the techniques you need to solve this. It'll be some combination of, looking at mod something, counting exponents, looking at bounding something. Yeah, so maybe I'll leave this. This is the kind of problem I think you should think about because there's a lot of steps, but they're all steps you know. So I'll take a few minutes to go over this problem 8. Because it's actually a very short problem. I don't okay, so what is it? You have this 7 to the 7 to the n plus 1. So this is the number. And you want to show it's a product of 2n plus 3 primes, maybe with repetition. So let's look at it. So so we want 7 to the 7 to the n plus 1 is a product of 2n plus 3 times. We want to show this with maybe with repetition. They don't have to be distinct primes. So right, so where do we start with this problem?
I was thinking of using the theory that if, for example, no, it's like it says that the Euler's function of n is equal to prime 1 to the power of, for example, let's say alpha minus 1 multiplied by prime 2 to the power of alpha sub 2 minus 1 and so on. But I have no idea how to add the powers to show that they're 2n minus 3.
What will you do with the Euler function? I'm confused.
There's an equation to it that is related to the powers of the primes.
Okay, but how will that? Like, I don't know any way to calculate the Euler function of this, right? Euler function in general, the only way I know to calculate it is with the prime factorization. Let me say this. When you see this expression, there should be something you do almost immediately with this expression.
Maybe say the evaluation of each prime that divides this expression by the listing exponent theorem.
Yeah. Okay. So one approach is by lifting the exponent, right? So what does it mean? So let's think. So but hold on. No, but let's see. If we want to use lifting the exponent, we would need the prime to be 7, right? Like if we wanted to get what's the point? So VP, if P divides 7 plus 1, then VP, or we can write as 7 minus negative 1. Then VP of 7 to the 7 to the n minus negative 1 to the 7 to the n, which is the same thing, is equal to VP of 7 plus 1. But okay, plus VP of 7 to the n. But okay, you see, it only works for P equals 2. And for P equals 2, I forgot what the form of lifting the exponent is. But you see, you can only use this for P equals 2.
Yes.
So it's and it will tell us that this doesn't have that many powers of 2. So it's not right, because
this so on the left with the 2 to the n, 2 times n.
Where?
We get that at least 3. So and for 2, so you're left with showing that we need 2n.
Okay, yeah. So maybe the 3 comes from the powers of 2, but okay, we need many more primes, right? So So the idea is whenever you see something like this, the sum of powers, generally you want to factor it. This expression actually factors very nicely. See, can you figure out how?
Seven to the n is an odd number, so it's 7 plus 1, which is 8, multiplied by, oh, never mind, it's very complicated then.
So but it
Or
helps if
no,
I
that
wrote,
could work.
what's the idea?
We have that since 7 to the n is an odd power, then we
Okay.
can use the formula, which is x plus y multiplied by x to the n minus 1 minus x to the n minus 2.
Yes.
And since y is
Great.
1 in our case, it's going to end up with 7 plus 1, which is 8, multiplied by 7 to the 7 to the n minus 7 to the 7 to the n minus 2 plus 7 to the 7 to something like that.
So are you suggesting factoring it like this? Or am I
Yeah,
showing
and
something
we
else?
then minus 7 to the 7 to the n minus 2 and so on.
And the last one will be -1, maybe, yeah? Okay.
It should
Maybe
be plus 1,
I
I think.
Yeah, I think it's +1, yeah, okay. Good, okay, we can do this. But we can do this. So then you'll get this one and you'll get this. Okay, I'll say something which is whenever you have an exponent which is a power. So for example, if I get something like x to the 8 minus 1, there's something I can always do I can take x to the 8 minus 1. Okay, I can factor it as x minus 1 times x to the 7 plus like this. But there's something you can do which is maybe a little bit more, will give you a little bit more, which is you can just say, okay, x to the 8 minus 1 is x to the 4 minus 1 times x to the 4 plus 1. Okay, but then x to the 4th minus 1 is x to the square minus 1 times x squared plus 1. And I have here x to the 4th plus 1. And then I can go even one more. I can go like this. Right, and the reason I can do this is because the power is is itself a power. Right, like the 8 itself is a power of 2. So there's something similar you can do here.
Maybe we take 7 to the 7 to the n plus 1. We take the 7 from 7 to the n, and we have it's equal vectors as 7 to the 7 to the n minus 1 plus 1 times some integer, and we do the same thing with this, maybe with 7 to the 7 to the n minus 1 plus 1.
Yeah, exactly. So we put like this plus 1, right? Because like this number is a 7th power, right? So we just, right? And then that times something like, okay, what will it be? It'll be 7 to the 6 times 7 to the n minus 1 minus.
But can't we use induction here?
Right, so great. So now, yeah, so now this is just so this is n minus 1, right? So you want to use induction, but okay, what should be the inductive step? So from here, we would have 2n plus 1 factors. So we need to get from here.
1, yeah. 2.
So from here, we have to get 2 factors, right?
2, yes.
So to do induction, we have to show that this number is not prime. Does it make sense?
Yes.
Why do we get that has 2 and plus 1 factors?
It's because if we were doing induction, right? So this is the same expression, but with n minus 1 instead of n. So if we knew the result for n minus 1, this would have twice n minus 1 plus 3, which is 2n plus 1 factors. Do you see?
Yeah.
We want to show that each time we get two more factors and that those two factors should come from here. Okay, so once we know how to factorize this expression, this problem, it becomes about understanding that this is not prime. Okay?
Maybe maybe we can look at it modulo 3.
Okay, so let's do, so let's rotate. Okay, so I want to show that 7 to the power of 6 times 7 to the n minus 1 minus 7 to the power of 5 times 7 to the n minus 1. Last one will be
I think it's
minus.
that will not be helpful because we will have it will be congruent to 1 mod 3.
Yeah, so mod 3, let's see what happens. Mod 3, can we get any factors out of this? Or can we get this to be 0 mod 3? So 7 is what mod 3? 7 itself is
So 1 mod 3.
It's one. Oh yeah, so these are all 1 mod 3, right? So then it's then we'll just have 1. Yeah, okay. So it's not, it won't work, right? Yeah, it won't work. So interesting. So here's one thing you could say. You could try to argue, you tried mod 3, but you could try like mod 5, mod 7, you could try a fixed mod, like 7, 5, 15, whatever. And what would you be doing then? You'd be showing that there's a fixed prime p that divides all of these numbers for all n, right? That could be an approach, right? Like, see if there's a prime p that always divides this.
But
yeah,
maybe that's not true.
Yeah, so let's try to determine, is that even possible? Could there be a prime that divides this always?
Wouldn't that be 2?
Besides, well, no, not in this case. It will be 2 will divide. See, okay. So what happens if I?
Oh yeah,
Like this number is odd, right? Like, so where are the 2s? So you're right, there are 2s. So where are the 2s? The point is, if I just repeat this over and over again, okay, so I'll get one term for each, like this, plus 1, and then we'll get another term that's like 7 times 6 to the 7 to the n minus 2, and then dot plus 1. And now all the way to the last term will be 7 to the power of 6 times 7 minus 2 to the plus 1. And the last term here will be 7 plus 1. If I just repeat this thing, right? So we want that each of these will provide 2, and this one is the one that
I think
that provides the powers. Yes?
Now we know that if n is odd, then we have x plus y divides x to the n plus y to the n. But can we extend this for like if we have x1 and x2 up to xm and we have n odd, then we have x1 plus x2 plus up to m plus up to xm divides x1 to the n plus x2 to the n plus up to xm to the n. If we prove that, then we are done here.
So you are saying maybe
by
it's
induction.
true that, yeah, I see. So you're saying maybe it's true that 7 to the, okay, so you're saying if, so it's a conjecture, that x1 plus xk divides x1 to the n plus xk to the n for n odd. Is this the conjecture?
Yes. Yes.
Let's see. So, well, let's do it for 3 terms. I don't know. So x plus y plus z, does it divide x to the n plus y to the n plus z to the n. Let's think. So let's even try 3, right? How would you even check something like this is true? So let's think. So here's something, right? So I'm not sure because what? So we can take x plus y plus z was like r. Okay. Now let's say we increase y by 1 and decrease z by 1, right? So we keep r, but we change like we okay. So we can do x plus 1, y minus 1, and z, right? So we can see what the change was from x cubed plus y cubed plus z cubed to now x plus 1 cubed plus y minus 1 cubed plus z cubed. So what was the change here? Change is the difference, right? The difference is 3x squared plus 3x plus 1 versus minus 3y squared plus 3y minus 1, right? So now this would be 3x squared minus y squared plus 3 times x plus y. I don't think that will always be divisible by r. I'm not sure. Let's see. Okay, so I'm not sure. Okay, I think the answer is no. And the reason I think it's no is because like how do we like here's one way you can show that x plus y divides sorry. Okay, let's do this. Here's one way to show that x minus y divides x to the n minus y to the n. Right? You can show that if x is congruent to y mod d, then x to the n is congruent to y to the n mod d. Does that make sense?
Yes.
And you can also do it for x plus y divides x to the n plus y, because if you have x is congruent to minus y and n is odd, then x to the n is congruent to negative y to the n. But I don't see a reason why if x plus y plus z is congruent to 0 mod d, I don't know why I would show that, for example, x cubed plus y cubed plus z cubed is congruent to 0 mod d. I don't think it doesn't, I don't see how why it would be true. I don't know. But yeah, maybe you can think about it some more, but I think the answer is no, that this is not this. I don't think this conjecture is true. But I don't have a proof really. But I think if you think about it, it's it won't be true.
Yeah, I think yes. Like we have x is congruent to minus y minus z mod x plus y plus z. Then we cube the both sides, and then we have some expression. If we suppose for contradiction that x plus y plus z divides this, then we have some expression of y and z is congruent to 0 with x plus y plus z, and then we can choose some x such that and y and z such that this expression is not congruent to 0.
Yeah, I think you're right.
Plus y plus
I think you're right because x has nothing to do with y. Like there's no x in the expression that results, right? So
yes.
Yeah. So yeah, you're right. So I think that's an argument. Yeah. So unfortunately, it's not true. Okay. So here's something I'll say because we really it's getting late and okay. So one thing I'll say is again, there was an approach where can we find a fixed prime? 3 won't work, but can you find a fixed prime that divides everything? I'll tell you now that that's impossible. That it's not true, and you can prove this basically by considering orders. Like, what are these factors? Like, what is this factor here that we wrote down? It's 7 to the 7 to the n plus 1 divided by 7 to the 7 to the n minus 1 plus 1. So you can think about this. It's kind of similar to the problem we were doing before, right? This is like it's not x to the 7 minus 1 over x minus 1, it's x to the 7 plus 1 over x plus 1. And so you can show that I think if p divides this, so I think if p divides this, I think it means that like 7 to the 7 to the n minus 1 maybe has order 14 mod p, I think. Something like this. Maybe I don't know. Something like this. I have to think about it.
Why?
Okay, maybe we can just do it. So let's try to understand. So we're going to understand, so okay, if p divides x to the 7 to the n plus 1 over x to the 7 to the n minus 1 plus 1, what does it mean? Let's actually not even do that. Let's just do this. X equals 7 to the 7 to the n minus 1. We want to understand p divides x to the 7 plus 1 over x plus 1. What kind of primes can divide this? So what kind of primes can divide this? So it means what? It means, first of all, x to the 7th is congruent to minus 1 mod p. So x to the 14 is congruent to 1 mod p. The order is 1, 2, 7, or 14. So let's think. Okay, so first of all, it can't be 1 or 7, right? Because then we wouldn't have this, right? So it's either 2 or 14. I think that makes sense. Yeah.
We could have b equal to, I think.
Ah, okay. Let's assume p is
That's
not.
fine.
Wait, sorry. You're saying p does not equal 2, let's say, right? I think that's okay.
Yeah, yes.
As long as p is
Yeah.
not 2, then we can eliminate 1 and 7, right? Okay. And in fact, p doesn't equal 2, right? Because we saw the number is odd. Okay, so now between 2 and 14, can it be 2? Well, if it's 2, yes, in the case that it's 2, we get x is congruent to minus 1, right? Yeah, because it's either 1 or minus 1, it's not 1, so it's minus 1, and then what happens? Then x to the 6th minus x to the 5th, this thing is what? This thing is exactly 7, right? I think that's true. So that would mean p equals 7. But okay, we know p is not 7 because yeah, we can see p is not 7. So that actually rules out as well too. Does it make sense?
Yes, so we have the order is 14.
Yeah, the order is 14, right? So what does that tell us? Okay, the order of 7 to the n minus 1 is 14. Okay. So now let's see, does that help us? We know P divides this if and only if that number has order 14. I don't know what to do with this. Can there be common factors? I'm not sure now. So here's the thing, right? So right. If so now let's consider So we know this is true, right? If and only if the order of 7 to the 7 to the n minus 1 mod p is 14. So what does that mean? It means that now let's say p divides, say, 7 to the 7 to the m plus 1 over 7 to the 7 to the m minus 1 plus 1 for m less than n. The point is then, it means that, okay, the order mod p of 7 to the 7 to the m minus 1 is 14. So if you take the order of something like this, where now n is bigger than m, that will be either, it has to be 2 now. The order must be 2. So in particular, p does not divide this bigger one. Does it make sense?
But what?
So we're saying, okay, let's say you have a prime divisor of one of the smaller ones, 7, like the smaller one for some m less than n.
Because
Then the order of 7.
Because the argument that says if b divides x to the 7 plus 1 over x plus 1, then the order is 14.
Yeah. So this one has order 14, right?
And this is 2. So b does not divide this.
Yeah. Does it make sense?
Yes.
Right, because I'm just taking powers of 7. So like when I take one power of 7, the order goes from 14 to 2, and then the order doesn't change anymore because I'm taking, yeah, you see? Yeah. Because then once the order is 2, it's either 1 or minus 1, and then you just take powers of 7 and it changes. It doesn't change anything.
Yes.
Yeah, so the point is, there cannot be a single prime that divides all of them. So you can never really succeed by guessing the correct modulus. Like I can't just guess 17 always divides. It won't work.
So could not we have some argument that proves that the original expression that we want to be composite? Cannot we have an argument that to prove it's composite?
Yeah. So what we need is an argument to show this is we want to show that this factors. And so actually what you do is something very clever. It's kind of like what you do with Sophie Germain. So you have something that you don't know how to factor, but maybe we can make it work. So what's the idea? What do we have? We have, so x is 7 to the 7 to the n minus 1. We have x to the 6th minus x to the 5th plus x to the 4th minus x. I skipped something. minus x plus x to the fourth minus x cubed plus x squared minus 1. Okay. And okay, so I don't know how to sorry. Yeah, so in general, this polynomial cannot be factored. Yeah, it cannot be factored.
I think you have missed some x here.
Did I? Yes, I did. Yeah, I missed. Yeah, you're right. Yeah, minus x plus
X and 1.
Yeah, there we go. Yeah, this polynomial can be factored in general. Yeah, I don't think it can be general. It cannot be factored in general because, well, okay, cannot be factored in general because, okay, if you substitute x by minus x, it becomes x to the sixth plus x to the fifth, okay, plus 1. And this one we had some argument. I forgot. Maybe during the polynomials chapter we showed. Did we show maybe Eisenstein criterion or something? I don't remember. I don't remember if we covered this. But okay, in general, this x to the p minus 1 plus this thing cannot be like cannot be factored in general. So like x to the p minus 1 or x minus 1 for p prime cannot be factored. But this isn't just the point of this is a special value of x. So let's think. So it's very similar to Sophie-Germain, where like in general you can't factor x to the fourth plus 1, but you can factor something like x to the fourth plus 4a to the fourth. So the idea is to consider consider what? So consider something like this. Let's take the idea is consider sorry, where did we go? You're here, yes. Okay, so consider this. What comes next? 6 times 5 over 2 is 15. That's 5 times 4, 20, I think. Okay, there's this. Okay, and then this becomes what? So minus now 7x to the fifth plus 14x to the power 4 plus 21 x cubed plus 14x squared plus 7x. And this thing is equal to 7 times x times x squared plus x plus 1 squared. Right. Okay. So this, okay, what does it mean? This thing, x plus 1 to the sixth minus 7x times x squared plus x plus 1 squared. Okay. And now, okay, because x is an odd power of 7, it's a difference of squares. And it can be factored. Does the argument make sense?
How's the last part? How can we vector this?
So because now this
last expression.
what happens? So the point is this one here, right? This is a square. This is also a square because x is an odd power of 7.
Okay, so it's a difference of squares.
Difference of squares, so it factor. You need to show one of the smaller factor isn't 1, but you can do that, and so then it's a difference of squares. Does it make sense?
So yes.
Yeah. So actually, this is the only solution I know to this problem, and yeah, so it's based on this factor. To be honest, I have no idea how you come up with this factorization, but okay, that's anyways, that's the solution. Okay. Anyways, yeah. But the idea is, it's a variant on Sophie Germain. Like, how do you what is the idea that lets you factor x to the 4th plus 4y to the 4th? Let's just write plus 4, right? The point is it's x squared plus 2 squared minus 4x to the square, right? The difference of squares. So it's the same idea, just much harder version. Okay. But yeah, that's the solution. It's a little bit miraculous, but yeah. Okay, so that's all for today. Yeah, I didn't cover one of the problems, but that's okay. Yeah, so I'll say about these problems, I for the homework problems, I sort of split them into 2 groups. So yeah, the first group, these 4 problems, I call them one-step problems, because they're really just well, they're one step. They're kind of like the warm-up problems. They're not, you don't really have to do, they don't take a lot of work. You have to be clever. You have to come up with that one, what that one step is. But once you understand it, it's a clean 1 or 2 line solution. Okay, so, and then the other ones are Olympiad problems. So they're like, you solve them by doing a series of one steps, right? Yeah, so you can submit either, but please try to work on these. They're roughly an increase in difficulty, and send me your solutions for whichever ones you want. But yeah, please send solutions this time because this will be the last number theory unit, so it'll be a good marker of like how much progress we're doing. In the next in 2 weeks we'll start geometry. Yeah.
Okay, thank you very much.
Yeah.